In the previous videos, we had given you a number and we were able to find the logarithm of that number. In the first, all the numbers were base 10. We could look at them as in scientific notation just as a power of 10. And in the second video, we looked at what happens when we had numbers in between the perfect powers of 10. But now we want to consider what happens when we have a logarithm and we want to convert that into scientific notation. So let's consider a couple of logarithms. So we know that the log of some number is, we'll call that x, is 6.00. The logarithm of another number is 6.40. And then we want to consider the numbers if the logarithms have been 7 or 7.40. And you'll see some relationships between these numbers as we head along. So taking a logarithm gives us the exponent of for the power of 10. What we need to do now is take the antilog, that's what your book calls it, the antilog to head in the other direction. But what the antilog really is taking 10 and raising it to the y power. So if y is the log of x, now we are going to take the numbers that we have in the logarithm column and make those the exponents of 10. So in the first case, we would take 10 and raise it to the 6th power. In the second case, we would take 10 and raise it to the 6.40 power. That's a little bit more confusing. It means that we have 6 full factors of 10 with an additional 0.4 factors of 10. Now, using rules of exponents, if I have a base to 1 power, let me actually write this to the side. If I have a base, like let's say 10 to 1 exponent power times 10 to another exponent power, we can say that since we have a factors of 10 in the first expression and b factors of 10 in the second, when we multiply those together, we will have a total of a plus b factors of 10. Well, we can think of 6.4 as 6 factors of 10 plus 0.4 factors of 10. So I can change this into 10 to the 0.4 and 10 times 10 to the 6th. Likewise, we can think of if the log is 7, that means that we must be looking at 10 to the 7th power. But if the log had been 7.40, then we're looking at 10 to the 7.40 power. Once again, we could express that as 10 to the 0.40 power times 10 to the 7th power. How does this help us? Well, we want to be able to figure this out in scientific notation. The top case is trivial. We know that if we have 10 to the 6th, that's just 1 times 10 to the 6th. If we have 10 to the 7th, we simply have 1 times 10 to the 7th. What we're interested in are these in-between cases. So you could simply, in your calculator, take 10 and raise it to the 6.4 power. And when you do that, you will end up with the number, if we round it properly, 2.5 times 10 to the 6th power. But you could get to this answer 2 different ways. It turns out we can just take 10 and raise it to the 6.4 power, or we can look at what we have here as 2 different factors of 10. The 10 to the 6th is exactly the 10 to the 6th that we had for the scientific notation. So the 10 raised to the 0.4 power, that means we have 40% of a factor of 10. So it's not going to be a whole factor of 10, it's going to be part of a factor of 10. It's sort of like the square root of a number is a half of a factor of that number. So 10 to the 0.4 turns out to be 2.5. Now the reason this is nice is because when you get down to the bottom case, you could take 10 and raise it to the 7.40 power. That's the easiest thing to do in your calculator. And by the way, you might notice on most calculators, if you have a log button, there's a button right above the log. It's usually the second function that says 10 to the x power. If you don't have that button, you can take 10 and raise it to the x power using the up caret symbol. This tells you that whatever comes after the up caret is a superscript on a calculator that doesn't have superscripts. So let's go back to the problem. You could simply take 10 and raise it to the 7.4 power, and you'll get 2.5 times 10 to the 7th. Now this looks awfully familiar because just a moment ago we got 2.5 times 10 to the 6th when we took 10 to the 6.4 power. Now why does this work? Well, because 7 could be thought of as 7 plus 0.4. So that means we have a factor of 10 to the 0.4 times a factor of 10 to the 7th. The 10 to the 7th corresponds exactly to the power of 10 in the scientific notation, and we already saw that 40% of a factor of 10 is 2.5. Not exactly, that's a rounded value, which we had before. Other things to note here, so note that's a little bit bigger than when we just had 10 to the 7th. Other things to note, when I went from a log of 6 to a log of 7, the number that we were looking at went up by exactly a factor of 10. Well, when I went from 6.4 to 7.4 for my logarithm value, it also went up by exactly a factor of 10. So the numerical part of the scientific notation was exactly the same, and the exponent went up by exactly 1. So if I were to tell you, we know that the log of 10 to the 6.4 is 2.5 times 10 to the 6th. 10 to the 7.4 is 2.5 times 10 to the 7th. So I could just continue that trend if I said, what is 10 to the 8.4 power? You would know that it's 10 times bigger than the 7.4 power. And so you would know immediately, if you knew what 10 to the 7.4 was, you would know what the 10 to the 8.4 was. Now let me go back and look at this all from the beginning, except this time we want to work with negative exponents, because when we work with concentrations, we're going to have small powers of 10, not large powers of 10. So let me write y equals the log of x, and this time we're going to start with a number of -5. We're going to look at -4.5. We're going to look at -4, and we're going to look at -3.5. So let's consider the anti-log, which would be x must be 10 to the y power. Okay, so it's very easy. We can write this must be 10 to the -5.00. This would be the other easy one is 10 to the -4.00, but the more complicated ones are 10 to the -4.50 and 10 to the -3.50. For the more complicated ones, it's actually helpful to think of this as, since we're working with negative exponents, to think about taking a half factor away from, let's see, we would want to look at this as from -5. I'm sorry, we would want to add on a half factor to 10 to the -5. And for this one, we would want to think of this as a half of a factor of 10, or 50% of a factor of 10, times -4 factors of 10. So just real quickly, adding a half factor onto -5 factors of 10 will get me to -4.5 factors of 10. In other words, we're dividing by 10 4.5 times, somewhere between 4 and 5 times. The same thing here, if we add up the exponents we will end up with -3.5. You'll see the reason that I wrote it as adding a half factor on instead of subtracting a half factor when you see what the results are. So if we write this finally in scientific notation, top row is going to be just 1 times 10 to the -5. Third row is just going to be 1 times 10 to the -4. And looking over at the logarithms, we dropped by 1. I'm sorry, we actually increased by 1. So we're going up. We increased by 1 in the logarithm, but we went up times 10 in our scientific notation. When we put in the numbers, if you raise 10 to the -4.5 power, you will see that you get a result of 3.16 times 10 to the -5. And if you take 10 to the -3.5 power, you get 3.16 times 10 to the -4. And this explains why I added a half instead of subtracting a half and worked with the -5, because that in this manner, the exponent, the full exponent, the integer exponent corresponds to the power in scientific notation, and the leftover fractional exponent is what gives us the digits in front. Okay, so 10 to the 0.5 power, which is actually the square root of 10, is 3.16. And once again, we see we have a 10 to the 0.5 power in this one, so we end up with 3.16 as well. And it's just that the power of 10 is different in the two cases. So if I had anything that was an integer and a fraction as the exponent, the digit part of the scientific notation would be 3.16. And the power of 10 is the only thing that would be different in each of the cases.